All right, this is okay, good. Well, thank you for having me. I know I had given the organizer's title, but I may have ditched that along the way. I want to talk to you today about a work to try and get to better identification of rare protein states in crystallography. All right, so the main thing that we try to do in a group is time-absorbed crystallography, right, where we apply, in our case, electric fields to protein crystals and try to detect excited states induced by electric fields. But especially during the pandemic, when we had time on our hands, we realized that a lot of it would carry over to cases like drug fragment screens, which is what I will mainly focus on today. All right. So often what you have in both time-absorbed crystallography and these fragment screens is that you have a mixture of states, and you try to detect a rare state, which means you have a relatively weak signal coming from the excited state, and most of the signals still come from the ground state. In addition, the signals are often subtle, for example, anomalous signal or limited coordinate shifts or small fragments. And at the same time, we often work in crystallography with a lot of sources of error. There's errors that come from upstream processing. For example, if your geometry is a little bit off, your integration is a little bit off. At the same time, you typically have variations in the beam, like a direction, intensity, wavelength, variations in the sample, absorption, and variations in the detector across the detected surface, for example. And finally, we have, well, not finally, but we have systematic variations in crystals when we're comparing crystals. They can be frozen slightly differently, or when used different humidity. They can be non-isomorphic, they can differ in the radiation dose, and in one example, that struck us in the redox potential. And finally, of course, there are random fluctuations that come from counting photons. So I'll try to get to three things. I can't promise I will get through everything. I'll first talk about how we work on correcting data for data acquisition errors, which just got published. Then I'll talk about corrections for crystal variation, and finally about extrapolation to full occupancy. All right, so first I want to acknowledge people did the work. Kevin and Jack did a lot of the work on crystallographic scaling emerging. Minwan and Phyllis did the work on correcting for crystal to crystal variation. And finally, Andrew, working with Harrison, has been working on extrapolating to full occupancy. And for some of the work on fragment screens, we've been working with Daniel Keedy and Tamar Millman at CUNY. And finally, we tried to post all of our software on the reciprocal space station. And yes, Kevin and Jack wrote a fancy diffraction predictor just to make the image, the logo. All right, so if I measure an intensity in one image and another image for the same Miller index, right? All we really know is the intensity. We know it's proportional to the structure vector amplitude squared, but this proportionality is not a constant, right? So if we measure 200 for one, we're on this green line. We measure 500 for the other, we're on the red line. But we can't say with confidence even that one is bigger than the other until we scale. So we need to know the scales. And to do that, I'll first give you a brief analogy, and then I'll explain how we approach that. As an analogy, you can think of your measurements like opinion polls about what's happening in the election, which is in your crystal. Yeah. But the issue, of course, is that the photons that answer the phone, so to say, not necessarily are the ones, are representative of what's happening in the crystal. Just like voters who answer the phone and tell you what they're going to do. It might be that they're not the ones voting, but it might be that the people who answer the phone are not representative of who will actually show up. So here's a different example of a badly scaled difference map, where you can see that the red and blue are kind of out of whack, and that can lead you to incorrect conclusions. And what people do in opinion polling firms, right, is they try to correct for that by registering the demographic attributes of the people who answer the phone and try to correct the mix to the mix that they expect to see on election day. So how do we correct data in crystallography? We use some combination of physical or quasi-physical models like this. But the key really is redundancy between different images, right? Where we have the same spot with the same Miller index in different images, should have the same structure vector amplitudes, but they typically don't have the same intensity, and that ratio is quite informative about the relative scale between images. So what Jack and Kevin developed is Careless, which is a machine learning approach to this. So instead of having the demographics of the voters, we have the properties of the photons that we count, which image with crystal and so on. And we try to use a neural network, in this case, from that to estimate the scales. Well, at the same time, we have to estimate the structure effector amplitudes. And you can see this is still not sufficient because we still have two things of which only we know the product. So as extra information, we need a statistical prior on the structure vector amplitude in this kind of an approach. All right, so I'm not going to review that paper. What I want to talk about is the case where we have multiple data sets that are related in some way. They're from different time points or from different fragments or so. Oh, sorry, I'm skipping ahead. What we do in the single crystal case, right, we use a well-known prior that has been around in crystallography for 75 or so years, which is the Wilson distribution, right? And what the Wilson distribution is based on is the assumption that if you look at the contributions of different atoms to the total structure factor, and you look in the complex plane, that the central limit theorem applies and that they're normally distributed in 2 dimensions. All right, so what we want to do now is, right, we want to exploit the correlations between data sets. Basically, the idea is if you have many data sets, but there's slight variations on the same theme, you get a lot of pseudo redundancy that you can exploit during scaling. And you want to do that in kind of statistically optimal way. And for that, you need a statistical model of how related data sets are distributed. So here's a simple example. We have structure factors of a PTP1B crystal in the absence of the inhibitor and in the presence of the inhibitor. And I'm plotting them against each other, and it's obvious that they're correlated to each other, right? So if I take some different bins here for different values of the apo structure factor amplitudes, you can see that it gives a fair amount of information about what the structure factor amplitudes of the inhibitor bound state should be. So we can make histograms. In blue, I'm showing the standard Wilson distribution, and it's a well-known result in other contexts in crystallography that these conditional distributions should be Rice distributions. And you can see the Rice distributions fit the observed structure factor amplitudes for the inhibitor-bound data set very well. So here's another example from time-resolved crystallography where the correlations tend to be even stronger. And we can use this information to condition scaling of the data. All right. So that's again the idea. I got ahead of myself. So colloquially in our group, we've been calling this the double Wilson distribution because essentially we started looking at pairs of data sets. We assume that the Wilson distribution applies for each separate data set. We assume that we can describe the correlations between different data sets using a single correlation parameter. It's a simplification, but a useful one. And finally, when we have more than 2 data sets, we can generalize this using something called conditional independence diagrams to contain a joint structure factor amplitude distribution that we can factorize. Yeah, there's some technical details I'm going to skip over. All right, so here's an example where on the top, what we did was we said we expect the freedom weights in this data set to be strongly correlated, but not identical. Yeah, so we can detect anomalous signal. So, and we did this for an actual data set of thermolysin, which has a catalytic zinc ion, which you can see here. And what you can see, if you scale the data sets independently, I mean, the freedom weights independently, you can detect the catalytic zinc ion, but not very strongly. And you detect it about twice as strong when you apply this expected correlation during scaling. And as a result, you can also detect the secondary zinc binding site that has been observed in a larger data set of the same protein. And here are some examples of calcium sites where we do a much better job detecting these calcium sites when we impose a prior expectation for the correlations between the freedom weights than when we don't do that. When we tune this expected correlation and see how the signal depends on that, we can see in this case that there's a clear optimal value of the expected correlation, about 0.99, that maximizes the anomalous signal. Yeah. All right. We did apply this to a very small subset of a much larger crystallographic direct fragment screen, 16 fragment-soaked dataset and 1 APO dataset. We applied the same expected correlation and jointly scaled the datasets. And you get fairly strong gains in the quality of the difference maps that you get. These are just isomorphous difference maps that you get from this kind of an analysis. Yeah, so the gains are about 80%. If we compare this to Panda analyzed data, we can see that Panda generally does a little bit better. But we can already, just from isomorphous difference maps, get signal that's comparable to what you can get out of Panda. Of course, you can still take these merged structure vector amplitudes and pass them through Panda. We haven't done that, but presumably that is going to be better still. Yeah. Now you may say 16 fragments is a very small data set, and it's absolutely true. We think we know how to do very large data sets using a successor to Keras that's called Abysmal. Kevin has a knack for choosing names. And we'd love to collaborate with anybody who wants to try and improve their scaling and merging of direct fragment screens on that. With that, I'm going to switch to the second topic, which is to try and correct for crystal to crystal variation. So in times of crystallography, we often meticulously interleave our data such that we minimize systematic variation across crystals or between the different conditions. So we don't have a lot of artifactual variation, and we can simply, in such a case, subtract the on from the off data, or other way around, and obtain the difference maps that we can work with. As you all know, in fragments, you tend to have much more systematic variation across crystals to deal with. So if you have a data set with a meaningful signal that you want to detect, the challenge is to find an appropriate reference, like here, that can serve as the reference point that you want to subtract. So we've been thinking about this in reciprocal space instead of real space. And the approach we've been taking goes a little bit like this. So we see that it tends to be, so these are not real data. Yeah, these are just make-believe data for now. What we want to do is we want to capture basically the blue distribution. So we capture the distribution of the things that systematically vary across crystals, like non-isomorphism, while at the same time finding within the distribution points that are suitable references to subtract, again, in reciprocal space. Neural networks are exactly meant for kind of approximating complicated distributions. And that's the approach we took. So the idea is to take our structure vector amplitudes of different data sets, to pass them through a variational autoencoder. What they do is they introduce an information bottleneck, which forces the neural network to ignore a lot of idiosyncratic details and focus on the things that systematically vary across a lot of crystals. And then we reconstruct data sets that we're going to treat as pseudo data sets, pseudo APO data sets, as APO set kind of mimics. So we literally put in all the data on the left, and we get out reconstructed structure vector amplitudes that we treat as a point of comparison. And so that's going to give us the reconstructed structure vector amplitudes over here are going to serve as a pseudo APO state. Yeah. All right. So, and the name, we call this VALDO for VAE-assisted ligand discovery, which obviously a play on finding Waldo, who's called Wally apparently in the UK. All right. Anyway, so once we've done this analysis, we can calculate pseudo APO maps, and we can do the subtraction. We actually do the subtraction in reciprocal space, but it doesn't really matter. And we obtain difference maps just like you would in time-resolved crystallography. Then we do kind of a pretty hacky approach of we take the absolute value, we blur it to give us big blobs that we use to detect our hits. So that part is a little bit primitive. You can think of these difference maps as being an analog of Z maps in Panda. And the other thing we do is we apply an approach from time-resolved crystallography, which is to do extrapolated structure vectors and calculate extrapolated maps. Yeah, and that's equivalent to like an event map. Yeah, so I'm going to call them Z maps and event maps for simplicity for now. All right. So if you kind of squint, what we're really doing is we're taking data MTZs with merged structure factor amplitudes and APO models. We pass it through VALDO and we get map MTZs and ranked blobs. So this is still a little bit of a work in progress, but we're slowly getting there. Benchmark is a PTP1B cryogenic fragment screen collected by Keedy and Fraser back in 2018, so quite a while ago. They deposited 1,680 data sets, and in the original report, they had 110 hits, where hit is a fragment with at least one discovered binding site. Helen and subsequently Helen and Daniel reanalyzed these data in 2 more papers and found an additional 59 hits. For some of what we'll be talking about, I will be focusing on fragments that contain at least one heavy atom. We've been kind of using those sharper peaks you can get from the heavy atoms as a reference for doing more quantitative comparisons. All right, so the first thing we did, actually not the first thing we did, but the first thing I'll talk about is we took the Panda refined models as deposited by the authors, and we just calculated the RCC with our event maps. And we see that our event maps very well capture the density coming from the models refined against Panda maps. And then we look at the difference maps. If you just look at FO minus FC maps, we do way better than FO minus FC maps, but nobody should be using FO minus FC maps to find fragments. When we compare to Panda, we tend to get sharper peaks, at least Panda S in 2018 as deposited by the authors, which means that the signal to noise ratio of these maps tends to be quite good. So we find more hits. We teamed up with Daniel and Tamar, because one thing I learned is when you try to rank your own hits, you'd like to believe all of them. So we asked them to cast a kind of a critical eye towards our hits. And so far, we've validated 30 of them. There's probably going to be a couple more once we're done with the full analysis. So of the hits we didn't find, 21, if we look at them, are supported by a maps if we look at them. It's just that we kind of, after looking at the first 300 data sets, not having the kind of fancy XCAM workflow, we were just like, okay, but that's enough for now. And 10 of them, we look at our difference maps and we don't find support for those hits in our difference maps. I'm not going to guess whether that's due to Panda or VALDO. Yeah. All right. And in general, we find also for existing fragments, we tend to find a lot more new binding sites that weren't seen before. All right, so this is kind of a preliminary map. It doesn't have all the new hits yet, but you can see that in some cases we discover new binding sites or extensions of existing binding sites that are exciting. In general, of course, we find most hits in known binding pockets, as I guess you would expect. All right, so one blessing and curse of kind of this analysis is that you end up with structure factor amplitudes for the bound state, which means you can do as much refinement as you want. Yeah, so it's instead of doing one round of refinement against a fixed real space map, in principle, you can just keep going and try to make things better, which is a hassle. All right, some examples of what you can do. We took some, we looked for some of these hits with, in this case, I believe it's a chloride atoms, I could be wrong. This was the originally placed model against the Panda event map. Here is in gray the VALDO event map, and in blue the VALDO difference map, which suggested to us that the ligand was incorrectly placed. And when we place it correctly and we perform refinement, we get a much better fit to the data. Here's another example where there was a fragment with a somewhat ambiguous shape placed here in the original Panda event map. We started refinement from this, where we have our event map and a difference map. And once we refine, we get something that looks like this. At that point, we suspected that the pose was wrong. And when we flip the molecule and refine a little bit further, we get an excellent fit to the data. All right, I know this is a little bit anecdotal, but this is where we are now in terms of working up the analysis. All right, there's a few caveats. We're still kind of in the beta testing stage. Your mileage may vary for your data set, and we don't have the whole fancy pipeline like you have in XCAM, but we believe that once you take our maps and your blobs, in principle, you can plug it into that kind of a pipeline and analyze things further. Sometimes what you have is outlier merged structure factor amplitudes that come from upstream data processing. And in bad cases, here's an extreme case, what you get is these Fourier ripples that make it hard for some data sets to see what's going on. It's not so common, but it does happen. I didn't put it here, but it's quite fast. If you analyze these 1680 data sets on a node with a GPU and something like 40 CPUs, it takes about 15 minutes to get from beginning to end. All right. I'm not quite sure how much time I have left. Okay, I have a few minutes left. So finally, I'll talk a little bit about a work on trying to get to maps with full occupancy of the excited state. Right, so in general, the problem is that what we observe is an average density, which is a combination of ground state and excited state. In Panda, essentially what you try to do is you subtract the fraction of the ground state, so you're left with the excited state. In time-resolved crystallography, what's traditionally done is you subtract in reciprocal space, analogously like the fraction you expect to be the ground state or the off state. In principle, neither approach is optimal if you have crystallographic data. Yeah, cryo-EM is a different matter. So Urs B. and Bourgeois, quite a while ago, already worked out a Bayesian scheme for what in principle is kind of the optimal approach to estimating the excited state structure factor. And you can see that it gets a little hairy. And not surprisingly, nobody has used this equation since then. What people have done are heuristic approximations of the ways that you can estimate from this kind of formalism. But it's 2026 now, and in principle, it is tractable to do this kind of integrals numerically. Yeah, so the way we did it, we used as our model for the probability of the excited state given the ground state, the same statistical model I talked about in the beginning, which gives you the probability of the phases and the amplitudes of the excited state given the ground state. And what we used is something called importance sampling to basically approximate these integrals. And you can do that pretty quickly now, maybe in like 10 or 15 minutes for a whole data set using importance sampling. Yeah, so we call this thing the double Wilson extrapolator. This is also, we're still finishing this work, but what you see here is we compared the best extrapolated map we get from this approach to the best extrapolated map by real space correlation coefficient to the excited state model that existed using extrapolate. And what you see in teal here is the electron density we get for the excited state when using for the ground state phases and the ground state refined model as a starting point. So basically, this is the starting electron density you get if you want to refine your excited state model against extrapolated structure factors. Yeah, and what you can see here rerun that. What you can see here in teal, right? This is the excited state chromophore over here, the picomeric acid moiety of photoactive yellow protein, and an arginine that gets shoved out of the way. And what you can see is that already, just starting from the ground state model and phases, that you get good support for the electron density of the excited state right out of the gate. Here's a second example, which is for photoswitchable fluorescent protein, where the green model is the excited state. And again, we get pretty good density here and here for the excited state, starting from the ground state model and phases. All right. We're still trying to. We have two adjustable parameters. One is the estimated occupancy of the ground of the excited state, and the other is the anticipated correlation between the ground state and the excited state. We can in principle optimize those. We're still trying to come up with like the most kind of the easiest kind of recipe for users to start with. The advantages so far that are quite clear is you don't have to worry about negative structure factor amplitudes. This is like doing French Wilson scaling into kind of 2 dimensions at the same time. Yeah, so you don't have to worry about that. And you don't have to do French Wilson scaling afterwards. And at the same time, we get R factors for the excited state model that tend to be much better than what we're used to. You know, sometimes people use FC as a reference in extrapolation, which kind of gives you arbitrarily low R factors depending on how you tune the occupancy. We're not doing it here. We're purely using observations to calculate the extrapolated structure factors. And we tend to get R factors in the 20 to 30% range instead of things that you tend to get by traditional extrapolation methods. All right, we'd love you guys to try this, of course. So where we are on these things, so this multivariate scaling approach is available in both careless, which is at this point well tested and easy to use. The only catch is that your data need to fit within the memory of a single GPU. Yeah, so large data sets are not tractable with that. Abysmal, which Kevin has been developing since, can apply the same statistical model during scaling and merging. The catch, there's no catch there. I guess the catch is that it's still under development, but the benefit is that there are no memory limitations and you can do arbitrarily large data sets. All right, so VALDO is coming soon. If you already want to test it, just let us know and we'll give you access. It's actually already, I guess, available online, but we can help you kind of get started. And finally, this double Wilson extrapolator is available currently on an experimental branch in RS Booster, which is an extension of Reciprocal Spaceship, and available for beta testing. Again, if you want to use it, we'd be happy to help you. So in summary, brief pitch for Reciprocal Space Station, where we have the software, we have Reciprocal Spaceship, we have Careless, and other software. And I mean, not just my lab, but also other groups that have been participating. So in summary, right, we see that if we model structure factor correlations during scaling and merging, it improves scaling and merging. We can correct crystal to crystal variation using this kind of VALDO approach where we do reciprocal space calculations, which are quite fast and quite accurate. And finally, we think we can get to better structure factors for rare states by using this kind of numerical integration approach instead of the current approximations. So far, all of these items have been separate projects by separate people, and we think that there's still more to be gained if we combine all of them in a single framework. And we'd be happy to collaborate with anybody who wants to try and work with us on that. And with that, I'm happy to take questions.
Paul Emsley, where am I from? Laboratory of Molecular Biology. 2 questions, if I may. Had I been involved in a data processing package and saw those ripples, I'd be rather disappointed. Have you had time to go back and look at where those ripples came from and see whether there's any
Yes. So for the case I showed you, which was one of the most extreme ones, what I did was I went back and for each Miller index, I looked at kind of like a z-score relative to all 1680 of them. And all the outliers were concentrated in a very small wedge in reciprocal space, which suggests that there was some issue there with incorrect masking or background correction.
Perhaps an ice ring.
Would have been an ice ring, yeah.
Well, you could tell by looking at the resolution.
Yeah.
Or, as could many people. Second question is that you didn't overly dwell on the methods that you were using. Can I ask you to take a moment to reflect on the prior art or crystallographic libraries that you had been using?
For
for the work that you've described here?
Oh, for all of it?
Isn't it related?
Yeah, okay, that's fair enough. So we've been developing some libraries ourselves to kind of interface crystallographic directly with crystallographic data with machine learning. Something we call reciprocal spaceship that kind of brings MTZ data, for example, directly into Python, so you can interact with things like TensorFlow and PyTorch. And it might be worth to emphasize, like 2 of the projects I described were led by undergrads. And the reason that's possible is because they know machine learning, they know Python. If you just give them access to the data, they can do it. And specifically we used, for further context, for the scaling emerging, we've been using TensorFlow, which was kind of, because at the time that we started, that was the most developed. We wish we had started with PyTorch, and for the other work I described, the VALDO work, we have been working in PyTorch. Yeah, and just to give you a sense of, again, the neural network just takes 5 minutes to run. It's the upstream and downstream stuff that takes a little bit of extra time, but that's all just parallelizable on CPUs.
Thank you. Thank you for the talk. Elspeth Garman, University of Oxford. We've been looking at metalloenzymes, and I wonder if any of your cases had metals in. We've done 100 now by proton-induced X-ray emission and found that 50% of them from the PDB have the wrong metals in them. When we put the right metals in, extra ligands that were not fitted before pop out. So that they were not modeled in the original PDB, but when you correct the metal, they come out. And I wonder if you have any comment about metalloenzymes and the effects.
The short answer is no. Just for the scaling emerging I talked about, right? There we can look at freedom mates and get anomalous signal, and that hopefully gives you some information about what metal you're looking at. When it comes to drug fragment screens, the only thing I can say is that in the case that we looked at, I think there were no metal ions of importance. I won't say that with 100% confidence. The one thing I could say is in that case, we used 2 different sources of apophases. We either started from a closed state, this has a catalytic loop that can open and close, or we started from the open state. And the results we get in both cases are highly correlated. So the phases matter, but they don't seem to matter